Oxidation-reduction reactions. These reactions involve a transfer of electrons from one reactant to the other reactant. They're also called redox because oxidation reduction is just a lot of syllables to say, so we call them redox reactions. Many of these types of reactions involve something reacting with oxygen, and here's some examples. Iron rusting, octane burning, hydrogen combusting with oxygen. So we have oxygen reacting with something else. Those are oxidation reduction or redox reactions. But you can also have ones that do not involve oxygen. Here's some pictures. This is a balloon filled with hydrogen and oxygen, and if you have a regular sized balloon that full with a mixture of hydrogen and oxygen, you touch it with a candle, it's going to make a very loud noise. And it'll probably bump the ceiling tiles up. And this hydrogen and oxygen mixed together, extremely flammable. Much worse than either of them alone. So, fireball. That'd be fun, but we're not doing that in class. Don't ask. Here's an oxidation reduction without oxygen. If you take sodium metal and react it with chlorine gas, you get table salt. Another example of dangerous elements reacting to form a pretty harmless compound. Sodium reacts violently with water. You drop a decent-sized piece in a sink of water, it'll blow the sink up. We're not going to do that in class either. Chlorine gas is very hazardous. You inhale too much of that, it'll kill you. But table salt is actually necessary for life. So let's look at these. Sodium reacting with oxygen, sodium reacting with chlorine. Both of these involve a metal reacting with a nonmetal. So something reacting with oxygen is a redox reaction. Something where you have a metal reacting with a nonmetal, that's going to also be a redox reaction. We can also look at these two particular reactions and see by looking at the atoms and the ions that form that electrons are being transferred. So here we have sodium atoms and we have oxygen atoms in diatomic molecules. And in the compound that forms, we have sodium ions and oxide ions. How do you make an atom into an ion? By adding or taking away electrons. And so that's what's happened here. The sodium has transferred electrons to the oxygen. Same thing's happening with sodium and chlorine. We start with neutral atoms and molecules. We end up with ions. The ions come about by the sodium transferring an electron to the chlorine. It makes a compound because the opposite charges attract each other. It's a transfer of electrons. It's a redox reaction. So here we have that one spelled out even more. The sodium atoms become sodium ions by losing one electron. This chlorine molecule will gain 2 electrons and make 2 chloride ions. Okay, oxidation is loss of electrons. Reduction is gain of electrons. So I had these deja vu brain fart moments. Have we talked about oil rig before? No? Okay. So oxidation is when a substance loses electrons. Reduction is when a substance gains electrons. And that can be difficult to remember. We have a lot of things where we have two names and 2 processes, and we have to keep them straight. You know, I have a hard time with that, so I've got all these little tricks. Oil rig is one that a lot of people use. Oxidation is loss of electrons. Reduction is gain of electrons. So if we look at this, here we have sodium going to sodium ion plus electron. It lost an electron. Oxidation is loss of electrons. Reduction is gain of electrons. So here the chlorine molecule is gaining electrons. That's reduction. Reduction and oxidation go together. If one atom is losing electrons, there has to be another one to accept it. There's no electron banks where you can just go and take a withdrawal and get some electrons. There are no homeless shelters for electrons. You can just have a direct exchange between two atoms. So they always go together. So any questions about that? So that's complete transfer of electrons making ions. We can also have an incomplete transfer of electrons, where the electron is not transferred from one to the other, but the electron density shifts and becomes lopsided. If we look at a hydrogen molecule, the two hydrogen atoms are going to share the electrons between them evenly because each of the atoms is the same. Here, two chlorine atoms in a chlorine molecule are going to share equally. But when you make the molecule HCl, now you've got little hydrogen and big chlorine, and they're not necessarily going to share those electrons equally. Okay, this is like older brother sharing a bed on vacation with little brother. And who's going to end up with more of the blanket? Big brother, because he's stronger, right? So chlorine is going to hog the electrons. The electrons are going to spend more time around the chlorine, and so they're partially transferred to the chlorine. It's not an ion, but there's a shift in the electron density. So we've got an increase in electron density for chlorine. Reduction is gain of electrons, or gain of electron density. You don't have to gain a whole electron, you just have to get a little bit more than the other guy. A decrease in density, electron density, is oxidation. Loss of electron density. Okay? It's hard to identify redox reactions between nonmetals. You can't look and say, oh, we had a metal and a nonmetal, we had atoms, and now we've got ions. We can see there's been electron transfer. You can't see that with nonmetals reacting. But oxidation-reduction reactions do occur between nonmetals. So we use what are called oxidation states. And this is just a thing that was made up to track electrons, to keep track of where the electrons are going before and after a chemical reaction, so we can predict which thing is being oxidized and which is being reduced. So oxidation states are not ion charges. They're imaginary charges, and they're assigned based on a set of rules. So the rules can be kind of confusing. The oxidation states, though, are frequently the same as ion charges. If something has an ion charge, the oxidation state is going to be the same number. But it's important to remember that ion charges are real. They can be measured. Oxidation states are imaginary. We've made them up. Okay. These are the rules, and the rules are followed in order of priority. And honestly, we got to set out the rules, but all of these, if you just think about ion charges, most of them take care of themselves. So if you have a free element, like sodium or chlorine, does it have an ionic charge? Cl2. Two chlorine atoms bonded together. Are there any ions in there? No. Their ion charges are 0. Their oxidation states are 0. If you have monatomic ions, like in sodium chloride, you've got sodium ion and chloride ion, then the oxidation state is the same as the charge. So that's convenient. In a compound, we've learned that the ion charges have to add up to 0, right? So in sodium chloride, we predict the formula by looking at the charges on the ions, +1, -1. We just need one of each, so the charges add up to 0. Oxidation states will also add up to 0 for a compound. Any neutral molecule, the oxidation states will add up to 0. If you have a polyatomic ion, that's a group of atoms that together have a charge. Then the oxidation states have to add up to the charge on the ion. So nitrate ion. we've got a nitrogen and 3 oxygens and an overall -1 charge. The oxidation states of each of these 4 atoms in there have to add up to -1. Metals always have positive oxidation states. Group 1 is always +1, groups 2 is always +2. Okay, that's redundant. That's the same as the charge that those take as ions. And then we have the nonmetals. This is where we've got something different here. So the order is listed in this table. And so we need to be able to remember this table, and it's actually not as hard as it looks. Do you guys know what pho is? Delicious Vietnamese noodle soup, right? Yummy stuff. Okay, pho, P-H-O. Like, well, how's that going to help? Well, what if we just do that? How would you pronounce that? Well, it's, a misspelled pho, right? Pho 765. I've been told that there's actually a restaurant here in Fresno named Pho 76. So we should make one Pho 765, and it's the rules for assigning oxidation states to nonmetals. Okay, so how is this going to help us? This is the order. Fluorine, hydrogen, oxygen. That's the FHO. Group 7, group 6, group 5. The oxidation states are the same number as the charge those elements would have if they were an ion. So basically we're looking at these nonmetals and we're saying, okay, you can't both have the charge that you want, right? Because if we look at, let's look at NH3. So ammonia is NH3. We've got 3 hydrogens and 1 nitrogen. If we think about ionic charges, the hydrogen would be +1. Oh, that's not a good example. That one actually works out. That's not right. I'm blanking. Yes?
If fluorine and oxygen, they're already in groups 7 and 6, right?
Mm-hmm.
Why are they on that list if they're already included in the groups?
Because they're special. Okay, here's a different example. PCl2. So if these got the oxidation states that were the same as their charges, chlorine would be -1 and phosphorus would be -3. And that can't add up to 0, right? You can't add a bunch of negatives and end up with 0. So we have to decide who gets what they want. And this is the order of who gets what they want. Fluorine always gets first pick. Fluorine wants an oxidation state of -1. Hydrogen gets second pick. If there's no fluorine in it, hydrogen gets what it wants, +1. Next is oxygen, and then after that, anybody in group 7, anybody in group 6, anybody in group 5 get what they want. Group 7 wants -1. That's the charge they have as an ion. Group 6 is -2, group 5 is -3. So the key here is the Pho 765. FHO 765 is their fluorine. He gets the charge he wants as the oxidation state. We can have fractional oxidation states. I don't know that we're going to run into any, but it is possible. It's not possible to have fractional charges because those are real things. But oxidation states are imaginary, and so they can be fractions. The sign is written before the number for oxidation states, after the number for ionic charges. I am not going to try to trick you with that, but I want you to know why the sign keeps going on the other side. So fluoride ion has a 1- charge, but it has an oxidation state that's -1. Teeny detail. Okay, examples. Hopefully this will help it to make a little more sense. So assign an oxidation state to each atom in each element, ion, or compound. We are assigning an oxidation state to each individual atom, not to the whole group. So in CR, what would the oxidation state of CR be? 0, because it's an element. You can look at it, there's only a single atom here. It doesn't have a charge. If there was a charge, it would be written. So the oxidation state is 0. How about the chromium-3 ion? The oxidation state will be the same as the charge. This is just a single atom. It'll be the same as the charge. So the oxidation state is +3. Let's look at CCl4. Here we have two nonmetals. We've got carbon and we've got chlorine. Fe765. No fluorine, no hydrogen, no oxygen. Group 7, yes. Chlorine's in group 7. It gets to pick before the carbon. What's chlorine going to pick? -1. Because if it was an ion, that's the charge it would have. So chlorine picks -1. Each chlorine has a -1 oxidation state. So we have one carbon and 4 chlorines, and the oxidation states totaled together have to add up to the charge on the molecule, which is 0. So I've got 4 chlorines, they're each -1, plus the carbon, don't know what that one is, and that adds up to the charge on the molecule, which is 0. So what's the question mark? It's got to be +4. So the oxidation state for the chlorine is -1, it's not -4. Each of them is -1. The carbon is +4. Any questions? So let's look at SrBr2. Is that a molecular compound or an ionic compound? Is strontium a metal or a nonmetal? Strontium's a metal. This is an ionic compound. So it's probably easiest to look at the individual ions. We've got strontium and we've got bromine. We know that bromine forms a -1 ion, and the strontium then must be +2. We also can tell that from its position in the periodic table. We have monatomic ions. The oxidation state is the same as the charge. So for strontium, what's its oxidation state? 2, +2. How about bromine? Each bromine is -1. Together, the two bromines have a total of -2, but each bromine has a -1. Just like each bromide ion has a 1- charge. SO3, 2 nonmetals. There's no ions here. Fe765. Fluorine, no. Hydrogen, no. Oxygen, yeah, we have oxygen. What does oxygen want to be? Pardon me? -2. How do we know that? Well, that's the charge it would have if it was an ion. It's not an ion here, but if it was an ion. So it gets its first pick, it wants to be -2. There are 3 of those. So 3 -2s would be -6. There's only 1 sulfur, so its oxidation state must be what? +6. We have 3 of these, plus 1 of those, adds up to the charge on the molecule, which is 0. It's a lot like ionic charges. Nitrate ion. Okay, so overall this has a -1 charge. So the oxidation states have to add up here to -1 instead of to 0. We've got nitrogen, oxygen, Fe765 again. Fluorine, no. Hydrogen, no. Oxygen, yes. Oxygen gets to pick what it wants. It wants -2. And we have to figure out what the nitrogen is. Well, we have 3 oxygens. That's a total of -6 from those. And so we need -6 plus the nitrogen has to add up to -1. So what's the nitrogen? +5. So the math is not hard here. We're just faking ionic charges for nonmetals. And we fake them by having this order of priority, which is based on stuff that we don't want to talk about yet, but it's based on some, it's not just made up, it's based on things, good things. Okay. So how do we identify redox reactions? We learned oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. If you have oxidation and you lose an electron, then your oxidation state goes up, right? Because you lose a negative electron, your oxidation state and your charge becomes more positive. Reduction is a decrease in oxidation state. Come on. Or a reduction in the oxidation state. If the oxidation state goes down, goes towards the negative, you have a reduction. So we can look at a reaction here between nonmetals, carbon and sulfur. They're forming CS2. Is this a redox reaction? How do we know? Well, we're going to have to look at oxidation states because there's no charges involved. Well, here carbon is an element, its oxidation state is 0. Sulfur is an element, its oxidation state is 0. In carbon disulfide, we do Fe765, and we find that sulfur in group 6 gets first choice, so it chooses -2. There are 2 of those, and those added with the carbon have to add up to 0, so the carbon's +4. Now we look at what happened from the reactant to the product. Carbon went from 0 to +4 in oxidation state. That's an increase. That's oxidation. Sulfur went from 0 to -2. That's a reduction in oxidation state. That was reduced. This is a redox reaction. So sulfur's gaining not whole electrons. It's not becoming charged, but it's gaining electron density. And so it's reduced. Questions? Use oxidation states to identify the element that's oxidized and the element that's reduced in the following redox reaction. First thing is identify the oxidation states. So SN, what's the oxidation state? Element by itself, 0. Let's skip that one. That one looks icky. This one, SnO2. Is that ionic? Yeah, it is. Can we identify the charges? Yeah, oxygen in an ionic compound is O2 minus. And based on the sum of the charges, we know that that's, the tin must be 4 plus. So the oxidation states here are the same as the ionic charges. So tin is +4, oxygen's -2. NO2, is that ionic? No. If you try to do it as ionic, you'll end up with nitrogen being -3 and oxygen being -2, and that can't add up to 0. So that should be a sign that, oh, wait a minute, I forgot something. Fe765. Fluorine, no. Hydrogen, no. Oxygen, yes. Oxygen gets first dibs. It wants to be -2. We have 2 oxygens. They're each -2. There's 1 nitrogen, so it must be +4. This 4 in front just says I have 4 of those molecules. It has nothing to do with figuring out the oxidation states. What about H2O? Who gets first pick? Hydrogen, Fa765. FH, what does hydrogen want? It wants to be +1. There's 2 +1s, so oxygen must be -2. Well, that's nice. Oxygen got what it wanted also. Water's a very happy molecule. Okay, let's go back to this one. Let's just do Fa765. Fluorine? No. Hydrogen? Yeah, there's a hydrogen. So the hydrogen gets to be +1. After hydrogen, the next in order is oxygen. Oxygen gets to be -2. This one is a little more involved. So we have 1 hydrogen, and we have 1 nitrogen that we don't know what it is, and we have 3 oxygens, and they are each -2. And what does this have to add up to? 0. It's a neutral molecule. So I've got 1 plus question mark -6 equals 0. So this is question mark -5 equals 0. So the nitrogen here must be +5. Any questions about that one? The math is not hard. You just have to remember what you're mathing, right? Now that we have the oxidation states, we can look and see what is changing. Start with the first one. Here's tin, and there's tin. So going from 0 to +4, is that being oxidized or reduced? That's oxidized. So tin is oxidized because its oxidation state went up. Here's hydrogen. Hydrogen's +1, and over here hydrogen's +1. It didn't change. Nitrogen is +5 here, and it's +4 there. That's different. The oxidation state went down, right? Went from 5 to 4. A reduction in oxidation state, so the nitrogen is being reduced. Not the HNO3, the nitrogen in the HNO3. Let's check the oxygen here. -2 goes to -2 and -2 and -2. Nothing's happening to the oxygen either. If there's oxidation, there has to be reduction. If there's reduction, there has to be oxidation. Any questions? So you have to have these simultaneously. If one is losing electrons, there's got to be another that takes them. So the reactant that reduces another element is called the reducing agent. The reducing agent is the element that's being oxidized. And the reactant that oxidizes another reactant is the oxidizing agent, and that one is being reduced. Well, that's not confusing at all, right? No, that's crazy confusing. I don't know why we have to talk about this, but we do. So let's talk about Hollywood for a minute. In Hollywood, California, you've got movie stars and you've got agents for the movie stars, right? Who stars in the movie? The agent or the movie star? The movie star. What does the agent do? The agent arranges for the movie star to be in the movie, right? The reducing agent arranges for something to be reduced. The oxidizing agent arranges for something to be oxidized. That make sense? The oxidizing agent does not get oxidized. It causes something else to be oxidized. So there's an opposite business going on. Determine whether or not each reaction is a redox reaction, and then identify the agents. So this first one, is this a redox reaction? We have a metal and a nonmetal reacting. It's a redox reaction. Here we can actually look at charges. In lithium chloride, the lithium has a positive charge and the chloride has a negative charge. That's from a previous chapter. We went from no charge to positive charge. We went from no charge to negative charge. We can think of this in terms of gaining and losing electrons. So lithium is losing an electron, right, to become a positive ion. Oxidation is loss of electron. So if lithium is being oxidized, it's the reducing agent. It's the opposite. So lithium being oxidized is the reducing agent. Chlorine is going from 0 to -1. It's gaining electrons. Reduction is gain of electrons. It's being reduced. It's the oxidizing agent. And if I were doing questions like this on an exam, I would be saying those words to myself in my head. I can't look at these and do this. Now, if this was all I did, sure, I'd be able to just recognize it. But I do this like, once a semester, so I get rusty on it too. Number 2, is this an oxidation-reduction reaction? Are things changing charges? Yeah. So in this one, we had things changing charges. It just wasn't all that obvious. Here, it's a little more obvious. Here I have aluminum, and there's no charge. And over there, I've got aluminum with a +3 charge. Here I've got tin +2 going to tin 0. So yes, it's a redox reaction. So we need to identify the agents. So aluminum. Aluminum is going from 0 to +3. Is that oxidation or reduction? Oxidation. So if the aluminum is being oxidized, what kind of an agent is it? Reducing agent. The other reactant is SN3+, going from +3 to 0. Oxidation or reduction? Reduction. So if it's being reduced, it's the oxidizing agent, because it causes the other thing to be oxidized. It gets reduced, but it causes the other thing to be oxidized. Stunned silence. It's okay. How about this one? Is it a redox reaction? It's full of ionic compounds, right? Are any of the ions changing their charge? No. This is a precipitation reaction. We're just swapping partners, and lead-2 and chloride happen to hit it off and precipitate. We've got lead-2 and nitrate. We've got lithium and chloride. Lead-2, chloride, lithium, nitrate. We're just swapping partners. There's no charges being changed. So this is not a redox reaction. Not all reactions are redox reactions. How about this one? Carbon reacting with oxygen to form CO2. Well, we got 2 nonmetals. We don't see any charges. Because we're dealing with nonmetals, we have to look at oxidation states. What's the oxidation state of carbon? Plain old carbon, 0. What's the oxidation state of plain old oxygen? 0. CO2, Fe765. Fluorine, no. Hydrogen, no. Oxygen. What does oxygen want to be? -2. So if oxygen's -2, what's the carbon? +4. There's 2 oxygens, they're each -2. So it's a total of -2 plus -2. Total of -4. 1 carbon, so this must be +4. So is this a redox reaction? Yeah, it is. Oxidation states are changing. So what's happening to carbon? It's going from 0 to +4. That's an increase. That's oxidation. It's being oxidized, that means it's the reducing agent. And what about O2? It's going from 0 to -2, that's reduction. So this is the oxidizing agent. The term oxidation originally came from something reacting with oxygen. So oxygen is often an oxidizing agent. Any questions? Isn't that fun? Oh, shoot, I thought we were done. We're almost done. Really, we are. Combustion reactions. Combustion, you've got something reacting with oxygen. This is burning. We know from life experience that you need to have air, which contains oxygen, in order for something to burn. So you've got something reacting with oxygen to make one or more oxygen-containing compounds. Combustion reactions also emit heat. That's why we burn natural gas, is to make the pot of water hot so that we can cook. So here we've got methane, CH4, reacting with oxygen. The oxidation states are given to us here. We see that carbon is going from -4 to +4. The carbon is being oxidized. Hydrogen is going from +1 to +1, not changing. Oxygen is going from 0 to -2. The oxygen is being reduced. It is a redox reaction. So, carbon dioxide and water. If you're combusting something that has hydrogen, carbon, and possibly oxygen in it, the products are always going to be the same, carbon dioxide and water. You need to remember that. If your reactant, the thing that you're burning, like this one, just has carbon and hydrogen, that's fine. It could also have carbon, hydrogen, and oxygen in it. It'll always give you CO2 and water. So we should be able to do things like this, write a balanced equation for the complete combustion of liquid ethanol, C2H5OH. So C2H5OH. We're told it's a liquid. If it's combusting, what's the other reactant? Oxygen. Oxygen's a gas. This has carbon, hydrogen, and oxygen in it. It's burning. It's going to make CO2 and water because that's what they always do. CO2, that's a gas. H2O, I won't try to trick you on this one, but if I'm burning something, is this going to be hot, cold, or room temperature? It's going to be hot. So what's probably the state of the water? It's probably a gas because it's so hot. Okay, so there we have it. Those are the reactants and the products. Combustion means reacting with oxygen. The only combustion reactions they'll ask you to predict are ones with carbon, hydrogen, and oxygen. It's always the same, CO2 and water. We have to balance this. So here's 2 carbons, and there's only 1 carbon here. So if I put a 2 in front of CO2, then I have 2 carbons on each side. Let's look at the hydrogens. There's 5 here and 1 over there. There's a reason that it's written that way. Makes it recognizable as an alcohol. Just, count up all the hydrogens. 5 plus 1 is 6. Over here I've got 2. So I need to put a 3 there to get 6 hydrogens. Now let's look at our oxygens. So I've got 1 oxygen in the ethanol, and I've got 2 oxygens there, and that needs to equal what I've got over here. So in 2 CO2s, I have 4 oxygens, and in 3 water molecules, I have 3 oxygens. So that's 7. 1 plus 2 does not equal 7. I don't want to mess around with the the coefficient on the ethanol, because that'll mess up everything else. I want to just mess around with the coefficient for the oxygen. I do have even here and odd over there, but I'm also adding 1, so it's going to be okay. Yeah, 3. If I put a 3 here, 3 times 2 is 6, plus 1 is 7. Balanced chemical equation. Any questions?